Are you able to see my PPT? Roll number 21.
Yes, sir. Yes, sir.
Audio is clear, na?
Yes, sir.
Okay, this is the problem we were discussing in last class. Okay, so here what we have liquid A. So this is liquid A in a cylinder. This is liquid A in a cylinder, and liquid A is evaporating in a gas stream which is having A and B. So height of the liquid is maintained at Z1. Height of the liquid is maintained at Z1, and this is the height of the you can say cylinder is Z2. You can think of origin is starting from the bottom of the this cylinder. So here we have origin at Z1, concentration is XA1, and at Z2 concentration is XA2. XA2 is given Z1. XA1 can be estimated by using Raoult's law, or you can say gas liquid interface. So saturated. So here at this interface there will be saturation concentration. So this is what equation we have derived. This is what equation we have derived, which is giving me variation of concentration with respect to Z. This is the variation of concentration with respect to Z, and this is the flux profile. So what will be the, you can see this flux is constant. Flux is not function of Z. Flux is constant. So whatever be the flux here will be same flux here, will be same flux here. Flux is not a function of Z. Flux is constant. So as soon as the molecule is evaporated here, whatever be the rate of molecule, so rate of molecule evaporated per unit time per unit area, that is nothing but the flux, that will be same throughout. So at the same speed it will transported and it will be mixed with a gas stream. So flux is constant. So flux is having this value. So this is what we have derived in last class. Anybody has any difficulty in this? So we'll try to simplify the equation mathematically. So nothing complicated, just a mathematical simplicity actually. Instead of writing this form of equation, we can write a different form of equation. So this is our NAZ. NAZ will be equals to C into DAB Z2 minus Z1 ln XA to XA. So 1 minus XA2, because this is binary system, 1 minus XA2 will be XA2 will be a XB2. This will be a mole fraction, total mole fraction of binary system XA1 plus XB2 plus XA2 will be equals to 1. So 1 minus XA2 will be equals to XB2, and similarly 1 minus XA1 will be equals to XB1 for binary system. So instead of writing 1 minus, we can write simply in terms of XB. And this is again flux of A in Z direction. This is flux of A in Z direction. Flux of B will be 0 because B solubility of B in liquid is negligible. As solubility of B is in liquid is negligible, hence NBZ will be equals to 0. This is NAZ in terms of NB, XB, okay, concentration of B. So for binary, as this concentration is decreasing as I am moving in from Z1 to Z2, concentration is decreasing. So concentration of B will increase. This concentration of B will increase. This is what, and the definition of ln XB2, okay, and this is what, so say you can see this is the what boundary conditions we have, okay, with these boundary conditions. So we got all this. Actually this is what we got the concentration profile, okay, concentration profile. Now this X, you can write this concentration profile also in terms of XB. This will give a concentration profile for B. For binary system, if this is given means it is as good as this is given. Because binary system XA plus XB equals to 1. If XA is given, it is as good as XB is given. If XB is given, it is as good as XA is given. So instead of writing this complicated form, so we can write like XB divided by XB1 equals to XB2 divided by XB1 plus to Z minus Z1, Z2 minus Z1. This is just simply we can write. This is also concentration profile for B, but using this concentration profile, I can get these also, because for binary system, it is very easy. So this is the concentration profile for B. So instead of calling this as a so concentration profile, this is also concentration profile, and these are related because XA plus XB equals to 1. So this is the simplified equation. So now we can calculate the average concentration. Okay, this is the average concentration variation, how the concentration varied average from Z1 to Z2. Because this is simplified, so initially we have written in simplified form, then we can get the average concentration variation. What will be the average concentration variation from Z1 to Z2? This is what average concentration variation. So substituting this XB here, okay, we can substitute this XB here. So this will be a average variation of concentration. If you substitute this here, so this will be a XB average will be equals to, you substitute it here, this XB equals to, and integrate from Z1 to Z2, and this will be over a length Z, average variation of concentration. This will be a XB2 minus XB1 divided by ln XB2 divided by XB1. This will be average concentration of B or average concentration of A. So one and same thing, because XA plus XB equals to 1. This is average concentration, and now this is average concentration. So if you correlate sometime back, you might have used a logarithmic temperature difference. So this equation looks similar. XB2 minus XB1 divided by ln XB2 XB1. This is called as a logarithmic average. This is also called as a logarithmic average or average concentration over the length. How the concentration is changing. So this will be average concentration over a length. This is called as a XB ln, logarithmic concentration difference. This you can say logarithmic concentration difference. You might have heard of previously logarithmic temperature difference. So based on this equation, XB2 minus XB1 divided by ln XB2 minus divided by XB1, that can be a term that can be called as a logarithmic concentration difference. Okay, so this is a logarithmic difference or logarithmic mean. So XB ln is a logarithmic mean concentration or logarithmic concentration difference. So now we can use this in a flux equation. So this is our flux equation. So here I have ln XB2 XB1, that will be equals to XB ln, so XB2 minus XB1 divided by XB ln, and substituting this, I will get, this will be a NAZ will be equals to C DAB Z2 minus Z1 XB ln. This is logarithmic concentration difference or logarithmic mean of the concentration, XA1 minus XA2. So actually I should get XA2 XB2 minus XA1, but XB2 is again 1 minus XA1, and this will be 1 minus XA2. So this will be a XA1 minus XA2. So this and these are equal. So XB2 is 1 minus XA1 XB1, and XB1 is 1 minus XA1. So substituting this and rearranging, so this is, you can say, a simplified flux profile, concentration profile and flux profile. So we can summarize this. Okay, so this can be written like this. Okay, so concentration profile can be written in terms of XB2 and XB1. Similarly, a flux profile can be written in terms of logarithmic mean concentration and XA1 XA2 or XB2 XB1. So this is the simplified form of flux. So now this is what we have discussed now. This is the basic equation which we derived. So this is the gas stream flowing at Z equals to Z2, concentration is XA2, at Z equals to Z1, concentration is XA1. If say instead of this, just I am not doing anything, same problem, just I can select the origin here. Okay, select the origin here, and whatever the remaining length of air through which this liquid is traveling, that is kept constant L. Okay, so this length is L. So Z equals to Z1 equals to 0 and Z equals to Z2 equals to L. So here will be a XA0. So concentration of A here will be a XA0. Here concentration of A will be a XAL. So what will be the concentration profile for this new nomenclature? Just the nomenclature is changed. What will be the concentration profile? Roll number 21.
Yes, sir. The concentration, here it will be increased, sir.
No, this is the concentration profile when my origin is here, and this is defined as a Z1. This is defined as a Z2. Now I am selecting my origin here because liquid level is kept constant. This is 0. Okay, this is Z equals to 0. This is Z equals to L. So here concentration will be XA0. Here concentration will be XAL. Just renomenclating the thing. So what will be the concentration profile?
Sir, it's like parabolic.
Give me the concentration profile. Everything is given on your screen.
Yes, sir. It's like same like Z2 L, sir. It's like same as like that, but opposite to it, sir. Like coming from top to bottom, like.
So what will be the concentration profile? This is my concentration profile, current concentration profile. You give me the concentration profile for this.
Yes, sir. It's here. It's like in the previous one, Z1 is like here X is equals to around 0.92. Here it's 0.1, sir. It's like instead of Z1, we'll get L, sir. L. Here it's L, no, sir. From 0 to L.
So what will be the concentration profile? That is what I am asking you. Give me the concentration profile for this. How XA will change with a Z?
Yes, sir. It's like. What do you mean?
What is it's like? It's like you give me the concentration profile. Na? What is here? Substitute Z1 equals to 0 and Z2 equals to
Z1 is equals to L,
substitute
sir.
XA1 equals to XA0 and XA2 equals to XAL.
L, sir. That's what I'm saying.
So that is what you need to pronounce the now concentration profile. What is new thing I am asking?
That's what I'm saying. So Z2 minus Z1 be L.
You give me the concentration profile, complete concentration profile.
It is equal to CAD by L into ln 1 minus X.
This is concentration profile.
Yes, sir.
No, sir. Concentration profile.
No, sir. No, sir. Instead of Z2 minus Z1, we have L.
Here, why? What is the concentration profile? Give me a complete concentration profile. Where you are sitting?
Hostel, sir.
So can you just show me your video? Show me your notes. Where is your notes? Hold it properly. People, it's best actually. Just give me a concentration profile now.
Yes, sir.
What is concentration profile? Here 1 minus XA divided by 1 minus XA0. So instead of 1, it will be replaced by 0. And here 1 minus XA2. Instead of XA2, it will be XAL divided by 1 minus XA0. And this Z1 is 0. It will be Z divided by L. So this is what concentration profile will be there actually. This is what concentration profile I will get. What is big deal in this? What will be the this flux profile?
NaCAD by L in ln 1 minus XA2 minus 1 minus XA0.
If not XA2, it will be XAL.
L, sir. XAL.
Okay. So just changing the nomenclature. Okay. So here, most important thing is this concentration profile and this concentration profile is not a different. Okay. This is same as that of this. This is same as that of this. Only the thing is here we are renomenclating as per change of origin. Here my origin was located here, hence this was nomenclated as Z1 and this was nomenclated as Z2. So concentration here, saturation concentration was given as a XA1, and here whatever be the concentration of A in a stream was XA2. So here now this concentration will be renomenclated as the XA0 and this will be XAL. So this flux, this profile and this profile will be same actually. This is not a different, just a renaming the thing actually. Renaming the thing as we are renaming the location as per location. Origin is here now. So this and these are same. Okay, this is not a difference. Okay, now solve this problem based on whatever formula we have derived. Solve this problem. This is what I have given you a modified or renamed flux profile and concentration profile, because here it is Z1 equals to 0 and Z2 equals to L. So consider a liquid which is water. This is water is evaporating into air, which is regarded as a binary mixture N2, nitrogen species 2 and oxygen species 3 at 1 atmosphere and 352 Kelvin. Take the air-water interface at Z equals to 0 and top end of the diffusion tube at Z equals to L. The vapor pressure of the water is 341 mmHg. Air is flowing at this temperature. Okay, this vapor pressure of water at this temperature 352 Kelvin. Air is flowing over a container which contains 10%, 75% and 15% water, nitrogen and oxygen respectively. If a diffusion tube has a length, okay, diffusion tube has a length L equals to 11.2 centimeters. So this is not a total length, okay, diffusion length. This is diffusion length is 11.2 centimeter. Give the temperature and at given temperature and pressure, diffusivity of water in nitrogen is 0.36 and diffusivity of oxygen, okay, diffusivity of water in oxygen is 0.36. Derive the equation for flux and find the value for a given case, neglecting solubility of N2 and O2. So you can see here, so diffusivity of water in oxygen is 0.36. Diffusivity of water in nitrogen is 0.36. So now as diffusivities are same, so for water, nitrogen and oxygen will behave similar as far as given data is concerned. Actually, it is not the case. This is as per given problem. Diffusivity of water in oxygen or oxygen in water is 0.36. Similarly, diffusivity of water in nitrogen or nitrogen in oxygen is 0.36. Both water is diffusing nitrogen and oxygen with the same extent. So for water, nitrogen and oxygen behave similarly as far as you are considering mass transfer. As far you are studying mass transfer, for water, nitrogen and oxygen are not a different species. They are same, because a diffusivity of water in nitrogen and diffusivity of water in oxygen is same. These are having same value. So I can consider this nitrogen and oxygen as a one species. Okay, as a one species, and you can call it as a air. So this A will be a water here, A will be a water here, or one will be water, and you can call it as second species which will be a air, because water diffusivity in nitrogen and water diffusivity in oxygen are same. As these are same, I can consider the nitrogen and oxygen is same species for water. For mass transfer of water, nitrogen and oxygen is the same. There is no different at all. if I am studying a mass transfer of water in nitrogen or mass transfer of water in oxygen. So I can take it as a mixture of nitrogen and oxygen as a species 2 and water as a species 1 and solve the problem. Already we have solved the flux, and what is there actually, what is derive the equation for mass flux. It will be exactly same. Mass flux equation will be similar as just now we have seen, considering a species 2 as a air, and then derive the equation and calculate what calculate nothing, air flow, vapor pressure, what is consider a liquid and this interface. So what is to be calculated? Air is flowing over container and this thing. So, and flux, you need to calculate the flux also, derive the equation and find the value for a given flux. What will be the value of flux? So what will be the equation you will be using? So this is what I was telling. So here water species A is evaporating into air, which is regarded as a binary mixture. Air, and this air consists of nitrogen and oxygen. Nitrogen and oxygen. So overall, I can take water is evaporating into air. Water is my one component and air is my another component. Because a diffusivity of water in nitrogen and diffusivity of water in oxygen is same. So this nitrogen and oxygen together is same species for evaporation of water. So I can take it as a water as a species 1 and air as a species 2. So because diffusivity of water in nitrogen is 0.36 and diffusivity of water in oxygen is 0.36. So hence, so it will be a water species A is evaporating into air species B. Okay, air species B. Now I can use this actually. So C DAB, diffusivity of A in B. So diffusivity of this is water in air. That will be equals to diffusivity of water in oxygen. That will be equals to diffusivity of water in nitrogen. Z2 minus Z1 is given. Ln XB2 XB1. So what is total concentration? How to get total concentration? Here roll number 23, Kaushik.
Yes, sir.
How to get total concentration?
So total concentration, like we'll get PA by RT, sir.
PA by RT or P by RT?
P by RT, sir. P by RT.
P by RT. P by RT is the total concentration. Okay, total concentration is P by RT. What is XB1? Here roll number 24, Bandi.
Yes, sir.
What will be XB1?
P
So what is the concentration of air here? First of all, what is the concentration of water here at the interface? Air water interface. What will be the concentration of water?
sir, it will be 15%.
15%.
0.9.
Here, Z equals to 0. Can you see my cursor?
Yes, sir.
So what will be the concentration of water at this interface? Water air interface. Roll number 25. So you people don't even know a small thing in chemical engineering, and you people have happily missed so many classes. Recently, you asked for a off because there was a sessional, end of the sessional, and you was not willing to take the class. And now if there is a compensation class is needed, now you people don't want to have compensation class and you are very much busy and you don't know how to get this small value. What will be the concentration? And this is not first time. In transport phenomena itself, you have estimated this value 10 times. What will be the concentration of water at this interface? How to calculate? Here roll number 25. Nivas? And don't think that if you are not switching off your mic means you got excuse from this question, okay? So it is taken as good as an interview or whatever the Viva question. Roll number 25, Nivas. Any input?
Six.
How to calculate the concentration at this interface? Very good. Roll number 26, Vijit. Roll number 28, Lalitha. Roll number 29, Vedant.
Sir, water concentration can be estimated there as P sat by RT.
What?
Sir, P vapor pressure divided by RT.
Very good. P saturated divided by RT. So concentration of water at the interface will be given by P saturated divided by RT. So how to get a mole fraction here? Nivas? No, not Nivas. Who was there? Roll number 29, Vedant. What will be the mole fraction of
Yes, sir.
A?
Sir, C by C.
C by
Sorry,
C,
CA by C. CA by C.
CA by C or P by P, P saturated divided by P.
Yes, sir.
Okay, it's simply P saturated divided by P will be a XA1. What will be XB1 then?
1 minus XA1, sir.
Yeah, what will
1
be
minus
XB1?
XA1. 1 minus
1 minus
XA1.
XA1 will be XB1. That will be a mole fraction of air. Not nitrogen or not oxygen. It will be mixture of nitrogen and oxygen. So XB1 will be a 1 minus XA1. And XA1 will be a P saturated divided by P. And what is XBL or XB2 here?
Sir, it's given XA1 is 10%. So we can have XB1 as 1 minus 0.9.
Yeah, it is given also. So it is 0.7 plus 0.5. Here XB2 will be a 0.9 and XB1 will be a 1 minus XA1 and XA1 will be a 1 P saturated divided by P. So substitute this value here and get. Now what is total concentration? C. What is the value of C you got? Vikram. Roll number 33, Vikram.
Yes, sir.
C, what is the value of C?
One, 1 second, sir. I'm calculating.
Oh, so 10 years before I told you how to calculate the C.
34.62, sir.
Yeah?
34.62 mole per
34.6
meter cube.
mole per meter cube. No, I think you are wrong. It is 3.462. You are wrong in somewhere actually, units. So 3.462 into 10 raised to minus 5 gram mole per centimeter cube. Okay, gram mole per centimeter cube. This will be a total concentration. So XB1, okay, XB1 is 0.9 and XB2 is 0.55. Okay, XB2 is 0.55, XB1 is 0.99. So it is taken reverse actually. Reverse. So XB1 is 0.99. So you can say XA1 is P saturated divided by P total P. That will be a 0.45. So this will be XB2 substituting this. So you will be getting N1Z. What will be N1Z value? Roll number 35. All other people who are getting this N1Z can write in a chat box. Write in a chat box your value of N1Z. Flux of water in Z direction. Roll number 35, Praneeth.
Hello?
What is N1Z?
1 second, sir, calculating.
Praneeth, can you switch on your video?
Yes,
Show
sir.
me
Yeah.
your notes. Show me your notes.
Hello?
Show me your notes.
Sir, am I visible?
No, now you are visible. Still
Yes, sir.
again gone. Show me your notes.
Sir.
So what calculation you are doing so long to get this
Sir,
N1Z?
sir, is it
Where
visible?
is N1Z? N1Z. Show me N1Z calculation.
Yes,
Flux
sir.
calculation.
Yes, sir. Yes, sir. I'm doing that. 1 second.
Where is? You have just written a problem. Just show me that your notes.
Hello?
Show me your notes.
Sir.
So where is your? You have not written anything. And what you are calculating?
Sir, NAZ, sir.
Where you are calculated? You have not calculated XA1. Where you are calculated XA1? Where you are calculated XB?
Sir, XB1 is 0.9. It's already given.
XB2 is? What is XB1?
Sir, XB1 is the concentration.
XA2. What is XA2? How to get XA2?
1 minus XB2.
And how to get XB2?
Sir?
How to get this 0.551?
1 second. Sir, like I am facing network issues, sir. If you see, I already left and joined again.
Excellent. Okay, this is what molar flux. Okay, you can switch off your videos. So this is what molar flux you will get. Now this is the problem. Now in previous problem, say nitrogen and oxygen having same diffusivity in water, or it is same. Water diffusivity in nitrogen and oxygen is same. But if in case these diffusivities are different, if these diffusivities are different, then how to handle this problem? Can anybody give idea in a class? If these diffusivities are different, so in previous problem, what we have done is this water having same diffusivity in nitrogen and oxygen. So nitrogen and oxygen is same species as far as I am discussing a mass transfer of water in nitrogen and oxygen. But say I am discussing mass transfer of water in nitrogen and oxygen, but diffusivities are different. This is water diffusivity in nitrogen is D12 and water diffusivity oxygen is D13. If this is the case, D12 and D13 are different, then certainly nitrogen, evaporation of water in nitrogen will be different, evaporation of nitrogen in oxygen will be different. Then how to handle this problem? Okay, then how to handle this problem? Can anybody give me input, any input? So there are two ways to handle the problem. Okay, there are two ways to handle the problem. First of all, say this is water is species 1, nitrogen is species 2, and oxygen is species 3. So this is the diffusivity of water in nitrogen. This is the diffusivity of water in oxygen. This is the diffusivity of nitrogen in oxygen. This is reverse diffusivity, and we know that D12 equals to D21. This you might have studied in Fick's first law of diffusion, Fick's second law of diffusion, and how to prove this. D12 equals to D21. Similarly, D13 equals to 331. D23 equals to D32. So instead of having 6 diffusivity, we will have only 2 diffusivity. Now I am discussing a diffusivity of water in nitrogen and oxygen. So these two diffusivities are important. So my species 1 diffusing in species 2 and species 1 diffusing in species 3. So instead of these two different diffusivity, I can use a effective diffusivity. Effective diffusivity. So and that will have effect of this diffusivity also, this diffusivity also. There are many arithmetic equation which will give you a effective diffusivity. There are many arithmetic equation people have proved, so which can be used to get the evaporation of species 1 into species 2 and 3 when these diffusivities are different. Instead of this diffusivity, so I can use the effective diffusivity and consider this species as a one species. So merge this species, mixture, this air, again air, and this effective diffusivity will have diffusivity of water in nitrogen and diffusivity of water in oxygen. Both effect it will have. One of such equation will be this. This is effective diffusivity will be equals to 1 minus XA summation of A not equals to I. A not equals to I, Xi divided by DAI. XA will be the mole fraction of species. Mole fraction of species. Okay. So which is diffusing XA, and Xi will be a mole fraction of species in which it is diffusing. So here A will be a water and I will be a nitrogen and oxygen, and I varies from A to I. So all I, so but I not equals to A, remaining Xi and a remaining diffusivity. So this will be diffusivity of 1, 2 and diffusivity of 1, 2. That summation 1 minus Xa, that will give you effective diffusivity. Once you have effective diffusivity, so instead, so you can use same equation, and instead of diffusivity, you will be using effective diffusivity, and this same equation, so you will be getting this concentration profile. This is the concentration profile, and similarly, you will get a flux profile. So you can see this is the concentration profile, exactly same concentration profile which we have derived previously. Concentration profile, there will not be any changes. Concentration profile will remain same. Only here you can say this is Z1 equals to 0, Z2 minus Z1 equals to L. So that is what according to a selection of geometry origin. Okay, and this will be a flux profile. How to select the and accordingly this I will get a flux profile actually. So if I substitute this here and get the value of flux profile, so you will get a flux profile. This is one way. And another way is I will select this differently actually. I will treat it as a differently. D12 and D13 is differently. So this will be a flux of oxygen in Z direction, flux of nitrogen in Z direction, and this will be a flux of oxygen in Z direction. So this is equals to 0, 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 this is equals to 0. So I can get variation of species 2 with respect to Z, variation of species 3 with respect to Z. Okay, this is variation of species 2 with respect to Z, rearranging this equation. Rearranging this equation, so I will get this equation, N2Z equals to 0, N3Z equals to 0. Similarly, here N3Z equals to 0, N2Z equals to 0. Rearranging this equation, I will get a concentration profile or concentration variation with, and this is integrating between the limits. This is integrating between a limit and substituting limits of integration. So this is the concentration profile for species 2. This is concentration profile for species 2. And similarly, I can get for species 3 also. Similarly, I can get for species 3 integrating this equation. And this is the concentration profile for species 3. And I know one fact, because this is three component system. XA1 plus XA2 plus XA3 will be equals to 1. This is one condition actually, and this is the concentration profile for species 2, this is the concentration profile for species 1. Using this, I can get the value of N1Z. So this is what the condition is there for this system for water, oxygen and nitrogen system. XA1 plus XA2 plus XA3 will be equals to 1. Now this is XA2, this is XA3 and XA1, that will be equals to 0. So XA1 will be equals to 1 minus XA2, this is XA2 and this is XA3. And I have one boundary condition. At Z equals to 0, this equals to XA0, X10. This I can calculate saturated concentration of water at the interface. Saturated concentration at the interface. That will be substituting Z equals to 0. So this will be Z equals to 0. This will be Z equals to 0. This is X2L. This is X3L. Now using these also and different diffusivity. So I can estimate N1Z. Okay, I can estimate N1Z. So here say diffusivity of water in nitrogen is 0.364 and diffusivity of water in oxygen is 0. These are different value. If these are treated as a different value, substituting all the value, what is X10? X10 will be a P saturated divided by P. Saturated pressure is saturated or vapor pressure is 341 and total pressure is 760 mmHg. So this will give me a X10, X2L is 0.75, X3L is 0.15. So and this L is 11.2. C, total concentration I can estimate P by RT, and this will be a diffusivity of water in nitrogen and this will be a diffusivity of water in oxygen. So these are the value, total molar concentration P by RT, and this will be X2L will be a 0.75. This will be a mole fraction of nitrogen in flowing stream. This will be a mole fraction of oxygen in flowing stream. This will be a saturated concentration of water at water-air interface, and this will be a length. Substituting everything, I can calculate the flux. So substituting everything, so the value of flux will be a this. Actually, this will be the value of flux. Anybody has any confusion in this? So there are two ways. First of all, you can calculate using this effective diffusivity also. So effective diffusivity, this will give me a flux profile and this will give me a concentration profile. So using effective diffusivity also you can calculate. Another way is you can use individual diffusivity. So this is the way, and you use the condition that X1 plus X2 plus X3 equals to 1. This is very important condition. So using this condition and individual diffusivity also, I can get the value of a flux. Okay, flux of water in nitrogen and oxygen, individual diffusivity, or you can use a effective diffusivity. This is clear to everybody? Any difficulty in this? Okay, now here the problem you see actually here, this was the problem. Okay, Z1 0, Z2 0. Consider system same thing continuously because of evaporation. If say Z1 is continuously decreasing, in all previous problem what we have seen is Z1 was constant. Z1 was constant, and somehow we are giving a liquid input of the liquid such that this Z1 was constant. But in this case, it is considered that Z1 is continuously decreasing because of evaporation. As Z1 is continuously decreasing, the value of Z1 is changing. So how to account for this variation of Z? How to account for this variation of Z? Anybody in a class have idea? And this is called as a moving boundary problem. Okay, boundary itself is moving. Boundary itself is moving. This is my system. This is where I am discussing the evaporation. The boundary itself is moving, and this is moving boundary. Boundary is moving. So how to account for this? How to solve this? Exactly, remaining thing is same. A stream of gas mixture AB, concentration XA2. Here XA2 is there. flow slowly over top of the tube, and fraction A is XA2 at Z equals to Z2. The entire system is kept at constant temperature and pressure, assumed to be ideal mixture, and B, solubility of B is negligible. Derive the expression for concentration profile and average concentration of gases. Only the thing is if Z1 is changing, remaining thing is same. If now Z1, because of evaporation, this Z1 is changing. So in such a case, so I know, so we are assuming steady state. So but steady state, this Z1 is constant. But now here I can assume quasi steady state. Quasi steady state means I will assume a less rate of evaporation, and in small interval of time, this Z1 is not changing. So considering quasi steady state, okay. So this was the initial case Z1 0. Say this is say Z1 0 at time t equals to 0, and this is Z1 t at time t equals to t. So this much liquid is evaporated in small t time. Small t time. So t is greater than 0. Say this is the initial height of diffusion length. This is the initial length of the diffusion, and this length of the diffusion is increasing. This length of the diffusion after time t will be a capital H plus HT. This will be a length of the diffusion. So to solve this problem, instead of considering a steady state means this will be also constant. I will assume quasi steady state. Quasi steady state is assume sufficiently smaller time in which this Z1 is constant. Okay. Instead of calling it as a steady state, I will call it as a quasi steady state. So time t equals to very, very small, such that variation in Z1 is negligible. Then I will get same flux profile. This is the flux profile, and this is the concentration profile. This is the concentration profile, and this is the flux profile. So this is the flux profile in quasi steady state. So exactly same thing. Instead of assuming steady state will be all the properties will be constant throughout the time. But in quasi steady state, in small interval of time, all properties remains constant. So this is very true when evaporation rate is smaller. Evaporation rate is smaller, the flux profile will be same. This will be a flux profile already we have derived. Okay, this is the flux profile. Now consider this. Okay, consider this and quasi steady state. I will get this flux profile. This is the flux profile. Now I need to relate with the time also. So what is this give me? This is the variation of height with respect to time. This is how height is changing with respect to time multiplied by surface area multiplied by density divided by molecular mass. What is this? If this is the variation of Z with respect to time, what will be this quantity? This will be a surface area. S will be the surface area. Rho A is the density of liquid, and Ma is the molecular weight of liquid. What will be this quantity? Roll number 35, Praneeth.
Hello.
What is this quantity?
So the whole quantity is kilomole per meter. Kilomole per meter, sir. S rho by MA will be.
Kilomole per meter.
S rho by MA, sir. Into meter per second. So kilomole per second, sir. Total.
Kilomole per. This is rate of mass transfer actually.
Yes, sir.
This rate of mass transfer or molar rate of transport of A per unit time. So this is meter. Say consider this is meter and this is kg per meter cube. This is meter square. So this will be kg and this will be a kilomole per kg. So it will be a this will be kilomole per kg per kilomole. So overall this unit will have moles per unit time. Okay, moles per unit time. This will give me a rate of mass transfer. How to get rate of mass transfer from this? Number 36 H.
Yes, sir. Some multiply by surface.
Yeah. So multiplied by surface area. This will multiplied by surface area will give me a again, this is flux multiplied by surface area. This is the rate of mass transfer. This is also rate of mass transfer. This is also rate of mass transfer. Now using this, I can discuss the variation of, I can get the variation of Z with respect to time. So I have assumed quasi-steady state, small amount of time. So where this flux remains constant, and that is related with Z1T. Z1T is constant during this small amount of time, quasi-steady state. So combining this equation, so I can discuss the variation of Z with respect to time. So this is what this thing. Now rearranging this equation and writing this equation HT, you can say this HT. HT is Z10. Z10 is constant, initial height of the liquid, and Z1T, this is variable. Z1T is variable, and this is what, and capital H is a Z2 minus Z10. This is constant. Okay, this is constant. So substituting this and rearranging the equation, I will get this. Substituting this and rearrange the equation. Substitute this and rearrange the equation. So you will be getting this equation. Now this is whole is constant actually. This is constant, and writing this as a 1/2c, half c. This constant as a half c. Integrating this equation and substituting this boundary condition at t equals to 0, height was, so you can 0, and at time t equals to t, height is h. Okay, this is which height? This is what height evaporation. This is rate of evaporation. Substituting this and integrating this equation. So, and this is what I will get. This is what height variation with respect to time. This equation is discussing height variation with respect to time. So this is clear how to handle when there is a variation because of evaporation, height is varying. In fact, I think same equation you have used when you might have done a Stefan's tube experiment in mass transfer. Have you done a Stefan's tube experiment in mass transfer? Here, roll number 37. Vignesh.
Hello, sir. Yes, sir.
Have you done
Hello,
a
sir.
Stefan's tube experiment in mass transfer?
Hello, sir. Am I audible, sir?
Yeah, you are audible. Have you done a Stefan's tube experiment in mass transfer?
Sir, which experiment, sir?
Stefan's tube experiment.
Yes, sir. Yes, sir.
So have you used this equation or similar equation? Maybe nomenclature might be different.
Sir, are you talking about the, I mean, h of t above equation or?
Okay, it's fine. So everybody is clear how to handle the problem when there is a height is varying and how to get this variable height actually. So using this, I can get a rate of mass transfer. HT can be correlated with the rate of mass transfer. So we'll solve this problem. Okay, take down this problem and solve at home. So diffusivity of gas, air, oxygen, and CCl4 is being determined by observing the steady state evaporation of carbon tetrachloride in a tube containing oxygen as shown in figure. The distress level is 17.1 centimeter. The total pressure is 755 mmHg. At temperature 0 degrees Celsius, the vapor pressure of CCl4 is 33 mmHg. Density is CCl4. Density is given, cross-sectional area. So this looks very simple actually. This is very simple. So this is NaZ. So NaZ, I can calculate, all the data is given. So flux of CCl4, this is flux of CCl4. Now I can use this flux profile. So using this flux profile, I can get a diffusivity value. So this will be a diffusivity value, diffusivity. This is what you have done in Stefan's tube experiment actually. In Stefan's tube experiment also you have done similar thing, you calculated the diffusivity. So if you go in more detail, so you can correlate the variation of height also.